So today's our last lesson, and it's polar functions day 2, okay? So we're gonna write parametric equations of polar curves, okay? Because this is gonna help us out, okay? So a lot of times we'll have, for a polar graph, we have r is equal to something in terms of theta, right? And then the curve defined parametrically becomes x equals r cosine of theta, okay? So this is just because cosine theta is x over r, so x would be r cosine of theta, right? And what that's going to allow us to do is we know r in terms of theta, and we're going to be able to replace this r with something with theta times cosine theta, okay? And then what we'll have is x in terms of theta, okay, over here. And we can do the same thing, the equivalent thing with y. Y would equal r sine theta. And then because r is equal to f of theta, this r can be replaced with f of theta, okay, sine theta. And so we're going to have over here, y would just equal something with theta, okay? All right. Now, slopes of polar curves, okay? So if we want to find, okay, if we have r is equal to f of theta, right? And we want to find dy over dx, then what we have to find is dy over d theta over dx over d theta. This is very much like parametric, and the reason is it's coming from this, okay? And the idea, instead of t, it's d theta we're taking the derivative of, okay? Now, I do want to say one thing, okay? This is to find dy over dx, okay? If r were equal to sine of theta, let me fix that. Okay, I want to make this really clear. Okay, and we wanted to find what dr over d theta was, we wouldn't have to do this. This is not for dr over d theta, okay? This is for dy over dx, okay? And so dr over d theta, that would just simply, well, here's r in terms of theta, right? So this would just be cosine of theta. Okay, so I want to make that really clear. This is for dy over dx. Dr over d theta is just what we've always done, right? It's just with r and theta. Okay, this is like dy over dx. It's the equivalent of that, where you're given y is equal to something with x. Okay. All right, let's do a derivative of one of these. Okay, so let's turn the page and do the first example. So I want to find the slope of the rose curve r equals 3 sine of 2 theta at the point where theta is equal to pi over 6, and then use it to write an equation for the line tangent to the graph, okay? So right off the get-go, okay, let's see. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So since this is pi, this would have to be 12 pi over 12. So each line is a pi over 12, right? So this would be pi over 12. This would be 2 pi over 12, but 2 pi over 12 is pi over 6. So we're talking about the point right here. So we're trying to find the slope of the tangent line to the curve right here, okay? Now, you can imagine looking at this, like we do know something, like this should come out, our derivative should come out to be a positive number, okay? All right, so what do we know? Well, we know that x is equal to r cosine of angle theta, right? And we know y is equal to r sine of theta. And then from our polar curve, right, we know that r is equal to 3 sine of 2 theta. So that would mean that this x is equal to 3 sine 2 theta okay, times cosine theta. And over here, y would equal, instead of r, we replace it with 3 sine 2 theta times sine of theta, okay? All right, so now to find the equation of the tangent line, I need to know the location. I mean, I graphed it, but I need to know the exact location of it, right? Because it's not going to be giving me a nice number right here, okay? Right? Okay. So at pi over 6, okay, this would be 2 times pi over 6 or pi over 3. Okay, so we're going to have x is equal to 3 sine of pi over 3 cosine of pi over 6. And then my y would be 3 sine of pi over 3 cosine of pi over 6. Not cosine. I do not know why I wrote cosine right here. It's sine, huh? Okay, because it's sine. Okay. All right, so sine of pi over 3. Now, it's really helpful if you can kind of do these in your head, okay, because you can go faster without drawing the diagram. This would be 3 times, and then sine of pi over 3 is the square root of 3 over 2. And then cosine of pi over 6 is also the square root of 3 over 2. And so this would make x equal to 3 times 3, right? So that'd be 9 fourths. Okay, so that's my x coordinates, 9 fourths. What's my y coordinate? Well, my y coordinate would be 3 times sine of pi over 3, and sine of pi over 3 is square root of 3 over 2. And sine of pi over 6 would be 1 over 2. So my y coordinate is 3 square root of 3 over 4. Okay, so now I know this point right here. Okay, and 9 fourths, that's just a little bit bigger than 2, right? Okay, and so that, yeah, because this is 2.5 right here, or a little bit bigger than 2.5. Okay, all right. So right here, I said a little bit bigger than 2.5, but I meant a little bit less, right? Because right here is 2.5. Okay, so the location of this point right here is 9 fourths, comma, 3 square roots of 3 over 4. Okay, now to find dy over dx, because I need that, right? I have the point now, right? We're going to find the tangent line at that point, but we also need, okay, the derivative, right? The slope of the derivative at that, or the derivative value at that point, okay? So we got to do dx over d theta. Okay, so dx over d theta, okay, we have to use this one, right? And we're going to need to use the product rule, okay? So this is going to be the derivative of the first function, okay? So that would be 3 times the derivative of sine, which is cosine. So this is going to be 3 cosine of 2 theta, okay, times 2, all right, times cosine of theta, the second function, plus 3 sine of 2 theta, and then the derivative of cosine theta is negative sine theta. Okay, so cleaning this up a little bit, dx over d theta would be 6 cosine 2 theta cosine theta. And then this would be minus 3 sine of 2 theta times sine of theta. Okay, so now let's find dy over d theta, right? Okay, so I'm gonna slide it up a little bit. So dy over d theta is equal to, and we're gonna have to take the derivative of this one, right? And so we're gonna have to use the product rule again. Okay, so the derivative of 3 sine of 2 theta would be 3 cosine of 2 theta times 2 times sine of theta plus 3 sine of 2 theta times derivative of sine theta would be cosine of theta. Okay, so dy over d theta would equal, this would be 6 cosine 2 theta sine theta These are a pain, okay? I'm not gonna lie to you. Okay, plus 3 sine 2 theta. They just take a while, okay? And then cosine theta. Okay, so I know that dy over dx, because I'm going to need that, right? Dy over dx is equal to dy over d theta over, let me slide this up a little bit, dx over d theta. And so dy over d theta is this, right? So 6 cosine of 2 theta sine of theta plus 3 sine of 2 theta cosine theta all over dx over d theta, right? And that's the 6 cosine 2 theta cosine theta minus 3 sine 2 theta sine theta. Make sure you can see the theta doesn't look like a 0. Okay? All right. So this dy or dx depends on the angle, right? Okay, so we got to do the angle pi over 6, right? So we're going to put pi over 6 into all of these. So we're going to find dy over dx, and that's equal to I should have put at x equals pi over 6. At x equals pi over 6. Okay, so that would be 6 cosine, and I'm going to do this in my head. 2 times pi over 6 would be pi over 3. Sine of pi over 6 plus 3 sine of pi over 3 cosine of pi over 6 all over 6 cosine of pi over 3 cosine pi over 6 minus 3 sine of pi over 3 sine of pi over 6. Okay. Okay, so cosine of pi over 3 would be 1/2. So this would be 6 times 1/2. And then sine of pi over 6 is also 1/2. Plus 3 times sine of pi over 3 is square root of 3 over 2. Cosine of pi over 6 is also square root of 3 over 2. Over, and then 6 times cosine of pi over 3. Cosine of pi over 3 would be 1/2. So 6 times 1/2. Cosine of pi over 6 would be square root of 3 over 2. Minus 3. Sine of pi over 3 would be square root of 3 over 2. Over 2. And then sine of pi over 6 would be 1/2. Okay, so this would be 3/2. Or let's go, I'm going to do it in fourths. So this would be 6/4. And this would be 3 times 3, which is 9/4. So plus 9/4. Over, and I'm doing this so that we get fourths. We're going to get fourths here. 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 And then we just can clear them out by multiplying top and bottom by 4. That's why I'm doing this, okay? So 6 square roots of 3 over 4 minus 3 square roots of 3 over 4. Okay, so then that would make this derivative be, and I'm going to multiply top and bottom by 4. So that's going to be 6 plus 9, which is 15. And this would be 6 square roots of 3 minus 3 square roots of 3, which would be 3 square roots of 3. And then cleaning this, well, 3 goes into 15, right? So it'd be 5 over the square root of 3, which is 5 square roots of 3 over 3. Okay, so there we go. That's the slope, right? Okay, so we can write it. So that's the slope. Okay, and we have our points from up here, right? So we can write our equation. So it'd be y is equal to our slope, which is 5 square root of 3 over 3 times x minus 9/4, and then plus your y, which is 3 square roots of 3 over 4. And there's your tangent line. A lot of work to get that darn tangent line this time, huh? Okay. All right. So that's how you do derivatives for polar curves. It's some work. Okay. Yeah, I'm gonna be honest with you. It is some work. Okay. All right. So let's go to the next thing, and we're gonna start talking about how do you find the area for a polar curve. Okay. So we don't use rectangles, which is a new thing. Okay. We got to think of a different way. Okay, guys, let's go to the next page. Okay, so this actually deals with something I taught you last year, okay? And it's this. It's the area of a sector, okay? And we're going to use sectors that have a radius, okay, and an angle to find areas of polar curves, okay? All right, so this is the center, this is my radius r, and this is my angle theta, okay? All right, so this is a full circle, okay? And for a circle, the area is equal to pi r squared, okay? But we don't have a full area for the circle. We just have part of it, okay? We just have this part of it. Well, that's a fraction of the whole, right? And so this angle theta is part of the whole angle 2 pi. So we can use that proportion to figure out the proportion of the area that I have, okay? So the area of a sector, okay, so the shaded region here happens to be the angle theta out of 2 pi, because that part of the whole angle that you have, right, theta out of the 2 pi, okay, that's going to be the same fraction of the area, right? So we can just take that fraction and multiply it by the area, pi r squared, okay? Okay, so we're going to do some rearranging. Okay, these pi's are going to cancel out. And so what we wind up with is 1/2 r squared, okay, times theta, because this pi and this pi cancel out. And I just put theta on the end, okay? And we did this last year in trig, okay? All right, so how does that manifest itself into this, okay? So what we have here is part of a sector, right? Okay, and this sector would have like this is a radius, this is a radius, and this is a radius. Okay, so this is analogous to rectangles. Okay, and this would be equivalent to like our heights of our rectangles. Okay, so this would be the right side, like the right side of a rectangle, and the left side of a rectangle. Okay, but they all come in polar. Instead of being a rectangle, it's a sector, okay? Because what we do is if we squeeze this down, right, these two together, and we make this angle get smaller and smaller and smaller, like we do with rectangles, we collapse the two sides, right? We make more and more rectangles, which makes them get squished together, right? So what happens is if we make more and more of these, right, within the same space, what happens is these two get squished together, okay? And in essence, you wind up with this like a line, and that's it. Like we do with rectangles, right? They come down, they collapse on each other and become a line. They do here too, because these two sides squish together. Well, what's squishing together is this angle down here, okay? So this angle is getting smaller and smaller and smaller, and that's our d theta, okay? Hopefully that kind of makes sense, okay? And this is my r, okay? So that'd be equivalent to my function height times your dx, right? Okay? Because if you put more and more of these in the same spot, these two sides are going to have to kind of and they're going to have to rotate together in this point and start to come together, okay? All right, so that's where this formula comes from, okay? The area of the region between the origin and the curve r equals f of theta, for alpha less than or equal to theta less than or equal to beta, okay? So this is like your RA and RB for rectangular coordinates, okay? Is the area would be the integral from alpha to beta 1/2 r squared d theta, okay? And then this r, like I said earlier, a lot of times we'll have r in terms of theta, right? Like r equals sine theta or something like that. And so we're going to be able to rewrite this r as a function of theta. So that's what this is, okay? All right, let's do a simple one right now, okay? All right, let's turn the page and we'll do our first example of this. Okay, we got to kind of analyze this a little bit before we jump in, okay? What we have to know is where angle theta starts, okay? So we're gonna find the area between 0 and 2 pi, okay? So 0 and 2 pi, but where does this start, okay? So I want to put in some simple angles that we can figure out cosine, because this deals with cosine, that we can figure out really simply in our head, some values to kind of understand, like, where does it start, where does it end, okay? So at angle 0, the start, right? Cosine of 0. Well, cosine of 0 is 1, right? And so 2 times 1 is 2, and 2 plus 2 is 4. So at angle 0, we're at 4. That's this point right here. Okay, so that's the initial point, or the start. Okay, we're starting at angle 0 right there. Okay, and then in essence, what we're doing is we're starting right here at the origin, and we're drawing a line to that, and then we're drawing a line next to it, and drawing, and that those are all little itty bitty sectors. Okay, all right. Well, and I should say, how do I know I'm going that way? Right? Sorry, I should have explained that. Okay. So I know, let's pick pi over 2, because that's an easy one to calculate. Okay, at pi over 2, which would be this one right here, right? At angle pi over 2, cosine of pi over 2 is 0. So that'd be 2 times 0, which is 0, so 2. So right here, we went from here at angle 0 to here at angle pi over 2. Okay, so we had to have gone this way, right? Okay, so we're going this way around this curve. Okay, how about angle pi? Well, that would be 0, right? So right here would be angle, would be another point, right? Okay, and then at, like, we could do 3 pi over 2, that would be 0, so it'd be 2. So this is the angle, this is the radius at angle 3 pi over 2. Okay, so you can tell we're kind of going this way, right? Then we come into the origin, and then we come back out. Okay, and then at 2 pi, right, cosine of 2 pi is 1, and we're back to 4. So we're back here at 2 pi, right? So we've covered this whole curve from angle 0 to 2 pi. Okay, so I'm going to cover this, finish it. Okay, so this is the start, but it's also the stop, right? Okay, so it's the initial point and also the terminal point, right? For this, because you're only graphing between 0 and 2 pi. Okay. All right, so in essence, what we're doing to kind of show you like how to create area, okay, we're drawing this, and that's a sector, okay? And then we rotate it just a little bit more, and we draw another sector, okay? And that's just a skinny sector. And I'm putting these, I'm stacking these up next to each other, okay? And look what happens, okay, is we start to create this area, right? If we, and I'm pretty far apart here, right? But what you're getting is you go around, right? You're going to collect this area, and this radius is getting smaller and smaller and smaller, okay? All right, hopefully that makes sense, okay? Now, a couple things you can do. A lot of times there's a lot of symmetry that's going on in these polar curves. So really, you could do it this way. I'm gonna go from 0 to 2 pi, okay? But we could integrate from 0 to pi and double it, and that would be the same as the area of this curve, okay? Because this top half and this bottom half are exactly the same. So if you only figure out the top half and you double that area, you would get the entire area. Okay, some people do it that way, and there's nothing wrong with that, okay? I'm gonna do it the whole way, okay? And we're gonna use technology to figure this out, okay? All right. Okay, so what I want to do is, I know I start here, I end here. There's no overlapping or anything, because we got to kind of worry about that, okay? And so we're going to integrate from 0 to 2 pi, and it's 1/2, okay, r squared d theta, right? Okay, but what's our r? It's this 2 plus 2 cosine of theta, okay? So this is equal to the integral from 0 to 2 pi of 1/2 times 2 plus 2 cosine theta, close the parenthesis, squared, and then d theta. Okay? And so that's going to give us the area of this sucker, okay? All right, just to save time, because I know this is going to take a long time for this video in its entirety. So I'm pretty confident you can put this in your calculator, okay? And what happens is you get out, I'm going to tell you, you get out 6 pi. It's exactly 6 pi, okay? But if you use technology, you won't realize it's 6 pi, okay? It's 18.850. That's what you get in the calculator rounding, okay? Hopefully that kind of makes sense. We did a simple one right now, okay? We're gonna get harder where we have to do the area between two polar curves, okay? That's gonna be a little bit hard, okay? All right, and that's kind of the next thing, okay? All right, you guys, I'm proud of you. Hang in there, all right? Okay, so for this one, example 3, is we want to find the area inside just one petal of the 8 petaled rose, okay? So let's start at angle 0, okay? And at angle 0, at theta's being 0 right here, okay? That'd be this right here, right? If we put it in here, that'd be 4 times 0, which is 0. Sine of 0 is 0, right? And 2 times 0 is, okay. So right here's where we're starting, right here at the origin, okay? And so we got to figure out, when does it hit 0 again, right? Okay. And if we can do that, okay, we know it hits at 0. We're going to be able to get just one of these. And I'm going to shade this in, okay? And I'm going to pause for a second and shade it in, and then I'll come back. Okay, so for this, okay, we know at angle 0, we're starting right here at the origin, right? I need to know, and basically we're coming up here, right? And we're going to come back. I need to know when it hits 0 again, okay? All right, so I need to solve 0 is equal to 2 sine 4 theta. Okay, that'd be equivalent of sine of 4 theta is equal to 0, right? Okay, so 4 theta is going to be, this is going to be 0 at 0. It's all, sine is going to be 0 at pi. It's also going to be 0 at 2 pi, 3 pi, also the negative ones if we need it, okay? Now, what I'm going to do to get theta is I'm going to take a fourth of these, okay? It's funny, I just taught this in Honors Math 3 today, okay? So, and it was our last lesson, or actually I taught it yesterday, okay? And it was like second to last lesson, okay? So I'm going to take a fourth of these, right? So that'd be theta is equal to 0, okay? That makes sense, okay? And then pi over 4, and then 2 pi over 4, which would be pi over 2, and then 3 pi over 4, right? Which would be, well, just 3 pi over 4. Okay, so this first petal right here happens between angle 0 and angle pi over 4. Okay, all right, and then another petal happens between pi over 4 and pi over 2, and another, because we're gonna get a petal every pi over 4. Okay, does that make sense? Okay, and you can, okay, that's one way of doing it. I just thought of another way. Okay, all right, so I know, okay, that there is 1, 2, 3, 4, 5, 6, 7, 8. 8 petals from 0 to 2 pi, right? Okay, so 0 to 2 pi, okay, if you divide that into 8, you get 2 pi over 4, right? Okay, and 2 pi over 4, 2 pi over 8, and 2 pi over 8 becomes pi over 4. So each one of these has to happen within a pi over 4 angle, okay? Hopefully that makes sense, okay? Okay, because that will tell me where I start integrating and when I stop, okay? All right? So I'm going to call this petal number 1, okay? Petal number 1. This one, okay, I'm going to tell you right now. In fact, I know this doesn't, okay? This one doesn't happen, okay, for between angle pi over 4 and angle pi over 2, okay, I actually think it's this one down here, okay? Because remember it starts here and it comes this, and then comes down, and then works like, you know, it kind of works its way around, okay? And here's why. Between pi over 4 and pi over 2, that would actually between pi and this would actually come out to be between pi and 2 pi, and sine is negative there, right? So yeah, it's going to be, you're going to get a negative radius, okay? So petal number 1 begins to be traced when theta equals 0 and ends when theta equals pi over 4. Okay, so here we go. All right, so we are going to set up an integral. It's going to be from 0 to pi over 4, and it's 1/2 my radius, and my radius is 2 sine 4 theta. So 2 sine 4 theta squared d theta. Okay, now this comes out, it's weird, this comes out to actually be, okay, pi over 4. Okay, if we did it all by hand, you would get pi over 4. Okay, I don't expect you to do it by hand. Okay, what you would get if you put this into the calculator is 0.785. Okay, so I'm not showing you the calculator today just to speed things up. Okay, all right. Okay, let's go to the next one. You know what? There's one more thing I want to say about this. Sorry. If I wanted the area of the entire thing, right? Okay, I could do 0 to 2 pi. Okay, I could do it that way. Or an alternative way is to do this and just multiply this area by 8, right? Because all of these are going to be the same thing. Okay, that's used a lot in polar curves. Okay, is that you use the symmetry of it and you just get one of them, and just how many are there? Oh, I'll just multiply by however many there are. Okay, and that's a way. So we would just put in, if we were finding the area of the entire um, 8 petaled rose, we would write 8 out here times 0 to pi over 4, and then we would get our answer that way. Okay, just wanted to point that out. Okay, so now we're going to get into area between two polar curves. Okay, and if we take the outer sector and minus the inner sector, okay, then what we'd be left with is the region between two polar curves. Okay, so really this comes, and I wish I had written this last. Okay, but this is really comes from the integral from alpha to beta 1/2. I'm going to say big R squared, okay, minus 1/2 little r squared, okay, and then times d theta, okay? So this is the sector of the bigger one, and this is minusing the sector of the smaller one, okay? All right, so for example 4 here, okay, find the area of the region that lies inside the circle, r equals 3, so that'd be inside the circle, right? And outside the cardioid, this is called a cardioid because it kind of looks like a heart, okay? This heart. So it has to be outside of this, but inside the circle, okay? So this right here, this region here is inside the circle, but outside the cardioid. This region right here, okay, all of this would be inside the circle and inside the cardioid, okay? This little moon, crescent moon shape right here, and we're gonna do all of these, okay? Over the next couple examples. Okay. This right here, this shape right here, okay, is outside the circle, but inside the cardioid. Okay, so there's different ways to describe it. Okay. All right. So at the very beginning, okay, where's the starting angle, right? Okay. So right here, okay, at angle 0, cosine of 0, okay. Well, angle 0, r equals 3 is this one right here, right? Okay. But for this one, okay, it would be 2 minus 2 cosine of 0, right? So it would be 0. This is the cardioid one, okay? And it starts right here, okay? All right, and I'm going to shade in I'm going to pause it and I'm going to shade in the region that we're talking about. Okay, so let me do that real quick. Okay, so we're talking about this red region, right? Okay, so what we need to do is we need to start. Okay, I'm going to tell you something. We want to start right here. I'm going to talk about it in just a minute, but we want to start right here, and we want to go with a counterclockwise angle. Okay, right? If you go this way, you're going to have problems. Okay, so we want to start integrating with this angle. So we want to start with a negative angle here. Okay, and go all the way, and then this is going to be a positive angle up here. Okay, all right. So from a negative angle to a positive angle. Okay, all right. Okay, so let's talk about this, okay? So I'm gonna kind of draw in the shape, okay? So right here, this is gonna represent like one of the sectors that we're talking about, okay? That's a really skinny sector, okay? So that's the outer one, okay? So you go from the origin going to the outer curve, okay? And then, so that's gonna be my big R, okay? And then if I go from here to here, right, the inner one, okay? And I take this sector right here, right? And I minus this sector right here, like the sector that's on top of it, right? Okay, this part right here, I'd be left with this. Okay, and that's the whole idea behind it. And we start making them here, and then we work our way all the way across. Okay, and this would be one of them. Okay, this actually right here at this point right here. Okay, both of these radiuses would be the same. Okay, actually, that's not true. Let me take that back. Okay, it's actually the blue one would be the full length and the red one would be 0. Okay, because this one, as we come up here, it's getting smaller and smaller and smaller and smaller. Okay, until right here at angle 0, it's 0. Okay. All right. So the very first thing we need to do, okay, is we need to figure out the intersection. We got to figure out these 2 points right here. Okay, what angles are those? Okay, so let's find the intersection of the 2 curves. Okay, so we know r equals 3, and we also know that r is equal to 2 minus 2 cosine of theta. Okay, at this point right here, both radiuses are the same. This point and this point, the r's are the same. You're the same on both these curves, the radiuses are the same. That means this radius is the same as this one, right? So we can replace this one with 3, and then we have 3 is equal to 2 minus 2 cosine of theta. Okay, I'm going to move the 2 over. Okay, and that'd be 1 is equal to negative 2 cosine of theta. Okay, that would give us cosine theta is equal to negative 1/2. Okay, and cosine of theta is equal to negative 1/2. Okay, so I'm going to list some positive ones. Well, hold on. Where is cosine going to be negative? Okay, it's going to be in the second quadrant and the third quadrant, right? So this is negative 1, right? And this is 2, and this is 2. This would be the square root of 3. This would be negative square root of 3. This would give you an angle of pi over 3, and this would give you an angle of pi over 3, right? Okay, so my point of this is this. You don't want to go from pi over 3, from 2 pi over 3 to 4 pi over 3. That's over in here, okay? So what you want to do is you want to start right here and go this way, right? So what's this angle? Okay, so we don't want to use pi over 3. We actually want to go this way, okay? So r theta would equal negative 2 pi over 3. We would start right here and start creating these and going around, right, until right here, okay? So this is going to be negative 2 pi over 3 to 2 pi over 3. Okay, this is just a suggestion, okay? I have this on my notes from previous years. okay, when integrating. Start with theta and rotate around in a counterclockwise direction. So you wouldn't want to start here with that angle and go to this angle, okay? You could start with this angle and go to here, okay? So you could, there's another way. You could do it from negative 2 pi over 3 to 2 pi over 3, okay? Now, I have to think here, but you could also start, you could start right here at 4 pi over 3, okay? Because this would be 4 pi over 3, okay? And go to 8 pi over 3. Okay, so you could go from 4 pi over 3 to 8 pi over 3. Okay, 4 pi over 3 to 8 pi over 3. You could do it that way too. Okay, so I don't want to think that's the only way. Okay, this curve right here is r is equal to 2 minus 2 cosine of theta. This curve is r is equal to 3. So right here, that's where we want to start integrating, okay? So we want to start integration at theta equaling negative 2 pi over 3. Start here, and we're going to work our way around to here, okay? I've said that several times, okay? We're going to stop the integration right here, okay? And just like you could have coterminal angles, right? That's why I'm saying this could start at 4 pi over 3, and a coterminal angle with 2 pi over 3 is 8 pi over 3, okay? So, I mean, that's why it works, okay? So we want to stop the integration at theta equaling 2 pi over 3. Okay, so my big R, my radius outer one, is 3, okay? And my little inner radius is equal to 2 minus 2 cosine of theta, right? It's the cardioid. It's the cardioid. Okay, so here we go. We are going to integrate from negative 2 pi over 3 to 2 pi over 3. I'm going to put the 1/2 like I did up here, okay? Hold on. Let's do it this way. I think I just messed up my whiteout. I did. I'll be right back. Okay, I'm back. All right, sorry about that. Okay, so this is going to be 1/2 times 3 squared minus 1/2 times 2 minus 2 cosine of angle theta squared, and then d theta, right? And I'm going to put bracket around this. And then, okay, so we could, because these both have 1/2 in common, right? We could pull it out because it's a constant. So this is equivalent, and that's what I started to write, okay? 1/2 times the integral from negative 2 pi over 3 to 2 pi over 3, okay? Of 3 squared, which would be 9, right? We can clean this up a little bit. 9 minus, and then 2 minus 2 cosine theta squared, and then d theta, right? And anything between this and d theta is what you're integrating, okay? So you wouldn't have to put the bracket here. I like it, but that's just me, okay? All right, and then you put that in your calculator, all right? And what you would get out is 14.077. Okay, again, I wish I could. I wish I could see you guys. I mean, this is a lesson where I like. There's a few lessons that we've done. It's like I wish I could see you, and you guys could ask questions because this isn't easy. Okay, it's hard to see because you just were introduced to polar curves yesterday, right? Okay, but what you have to realize is like I'm starting right here, okay, with my first sector, right? And I'm going to start making my sectors going all the way around, okay? Now, if I started right here, I would just have a full circle, right? Or not a full sector, but a sector of a circle, right? If I went all the way around and disregarded this um, um, cardioid, right? Okay. So then, okay, so that I would have the circle, right? Okay, so then I got to minus the part that's the cardioid, and then I'd be left with just this region right here. Okay, so basically, what's the outer shape? The outer shape is the circle, right? That's why this is 3 squared. And what's the inner shape? Well, for here, it's the cardioid, and we want to start here and go to here. Okay, so you could start with a positive angle, but then if you started with a positive angle, this would have to be 4 pi over 3. And then what would this be if you started here and got a big, this angle is going to have to be bigger then, right? Okay, so if you started with 4 pi over 3, this is going to have to be 8 pi over 3, okay? All right, so the difference between these is always going to be 4 pi over 3. Okay, I'm going to shut up now. Okay. All right, you guys, let's go let's go to the next problem. Okay, so almost the same problem, okay? But this time we want to find the area of the region that lies outside the circle r equals 3 and inside the cardioid r equals 2 minus 2 cosine theta, okay? So, okay, outside the circle, inside the cardioid. That would be, this is all outside the circle, right? So that would be this little moon shape, okay? So I'm going to color this in, all right? That's the reason they're talking about, and we'll get back. Okay, so what we're going to want to do is we are going to want to start right here at this point and work our way around this way, right? Okay, so we just figured out from example 4, right? The intersection of these, right? This angle was 2 pi over 3, right? Okay, now, and we wanted to start here and go this way on this last one, right? But this time we want to go here and go this way, okay? Because we really want to go in a counterclockwise direction as we create these, okay? And the reason is, okay, is that then you're going to go from a smaller angle to a bigger angle, and you'll get your limits of integration right, okay? Because if you go this way, if you go counterclockwise, you're going to go from a smaller angle to a bigger angle, okay? And that's what we need to do, okay? Otherwise, things are going to get messed up, okay, if you go the wrong direction of integration, okay? So we're going to want to stop it right here, okay? Now, this is negative 2 pi over 3, right? We did that earlier. But this time I don't want it to be negative 2 pi over 3. I actually want it to be 4 pi over 3. So I'm going to use theta is equal to 4 pi over 3 because this is the angle I'm starting with, and the one I end up with has to be bigger, okay? So hopefully you understand that, okay? So this time, the outer radius, okay, I'm going to try to draw this, okay? This is actually going to be a little bit easier to see. Okay, so that's the outer one, right? And that's going from the origin to the cardioid, right? Okay, so my big R this time is going to be equal to 2 minus 2 cosine theta, because that's my outer radius, right? Okay, and now my inner radius, my inner one is going to be to the circle. Okay, so my little r, my inner radius is going to be 3. Okay. All right. So, I'm laughing at myself. I almost asked, "Do you guys get it? Are you okay?" Like, and I was wanting the response. Okay. Oh my gosh, I'm losing my mind. All right. Oh, please be laughing with me. Okay. So we want to integrate starting here, and we want to go around this way. Okay. That's my whole point, okay? And we're going to end it right here, okay? Okay, so this would be the area. I'm going to slide it up a little bit. The area would equal, you guys must think I'm so weird. Okay, 2 pi over 3 to 4 pi over 3. And it's 1/2 our outer radius, which is the cardioid, right? So 1/2 times 2 minus 2 cosine of theta squared minus 1/2 times 3 squared. I'm going to put a bracket around it. And then d theta, okay? And then, okay, so what I would do, okay, just to make it a little bit easier to put in your calculator, pull the 1/2 out, okay? Let me slide it up a little bit more. Okay, so this would equal 1/2 times the integral from 2 pi over 3 to 4 pi over 3. And then 2 minus 2 cosine of theta squared minus 9, right? And we could put a bracket in here. And then d theta. Okay, and you'd put this in your calculator and you would wind up with 4.653. Okay, you know, I actually want to, I realized I wish I had put the arrows on the last problem. So let's go back to example 4 real quick and let's put the arrows on that. So we started right here at this point and we went around this way, right? And then we ended it. We ended the integration right there. Okay. All right, that's it. Let's go to the next, let's go to example 6. Okay, so this time we need to find the area of the region that lies inside the circle, r equals 3, and inside the cardioid, r equals 2 minus 2 cosine theta, okay? So inside of both, right? So inside the circle, but also inside the cardioid, right? So this, we wouldn't do this region, okay, because that is outside the cardioid. We wouldn't do this region because that's outside the circle. So we're talking about this region in here, right? This little region in here, okay? So let's go ahead and I'm gonna pause it and I'll shade it and then we'll, okay. So what we're talking about is this red region, okay? And in this case, all right, we're looking at the area in between the curves, right? But there's no area between the curves. It's just completely inside one or the other, okay? So like this was between two curves, right? This was between, there's no curves in between here, right? Okay, because you're inside of both. And what we have to do is we have to break this up into pieces, okay? So what we have to do is right here, this part right here, starting at angle 0 to this angle right here is only the cardioid part, okay? So I'm gonna draw a line here. I'm gonna break this up, okay? Okay, so right there, this, we could just find the area of the cardioid from this angle 0 to this angle 2 pi over 3, okay? And we could find this little section right here, okay? And then we could integrate, now this part is just the circle, okay? So we could find this circle and we could integrate it, or you could just do the area of the sector area of a circle, okay? Because it's a circle, okay? And you actually could, we could stop all of this at pi, because we know that this part of it and this part, there's symmetry, right? So if we got this area and doubled it, we would get the whole thing, okay? Now, I'm not gonna do it that way, but that would be a perfectly valid way of doing it, okay? All right, so I'm gonna go from here to here, okay? So from here to here, all right, and I'm gonna go along this region right here, okay? We're actually gonna go this way, right, until right here, and then we're going to pick up a different curve, okay? And this is the circle, and we're going to integrate to here, and this is where we're going to stop the circle, and then we pick up the cardioid again, and we're back here to 0, okay? When theta is 2 pi, right, cosine of 2 pi would be 1, And so that would make this 2 minus 2, which would be 0, right? Okay, so, all right, this angle, since we want to go from here to here, I'm going to call this one 2 pi over 3 and this one 4 pi over 3, okay? So this is going to be theta is equal to 2 pi over 3. And I did these all differently. I mean, it's the same one, right? But I did them all differently so you get this idea of what's inside, what's outside, and heck, there's nothing inside and outside, right? Okay, and so this one is 4 pi over 3. And the start for this one, right? The start, then the initial point, I would be theta is equal to 0. But then when you end it, theta is equal to 2 pi. Okay. And so, okay, so let me say one thing. You wouldn't have to use calculus to get this region right here. I'm going to, but you wouldn't have to, okay? Because it's a circle, right? With radius 3, okay? And so you could figure out this angle right here because you're going from 2 pi over 3 to 4 pi over 3. That's a difference of 2 pi over 3. So this angle right here is 2 pi over 3. There's your angle theta, right? It's just a sector, okay? Like we did in math 2, or not math 2, honors math 3, okay? Okay, so here we go. Okay, so the area is equal to the integral from 0 to 2 pi over 3. Okay, and then 1/2 2 minus 2 cosine theta, because it's the cardioid, right? 2 minus 2 cosine of theta squared d theta. Now, if you doubled it, that would give you this area, and then you wouldn't have to do another integral for this one, right? You could do it that way, okay? All right, and then plus, okay, the integral from 2 pi over 3 to 4 pi over 3, and the 1/2, the radius, right, which is 3 squared, okay, d theta. And then, okay, so we've gotten this region right here, we've gotten this region right here, and now we need to get this region right here, right? And to make it, we have to go from here to here, okay? All right, so plus then the integral from 4 pi over 3 to 2 pi of 1/2 times 2 minus 2 cosine theta squared d theta. Okay, and that would give you an area of 14.197. Okay, if you just put it on your calculator, okay? All right, guys, hopefully that helps, okay? That's it for example 6, okay? And that's the last example, guys. That's the last calculus problem with me, okay? You guys are gonna go on and do great things, all right? You guys are gonna be great, all right? Thank you so much for taking BC. I really appreciate you, because this pushes me, this pushes my math skills and everything else along with you. So I always appreciate when I have the chance to teach BC. So I really appreciate you guys, okay? And I really miss you guys. All right, you guys, you take care. Bye-bye. All right, you guys, so for today, the polar functions day 2, what I want you to do is page 565, 39 through 59 odd, okay? And that's the last assignment, okay? All right, you guys, I actually said goodbye to you and I forgot I had to do this, so I get a second goodbye. Goodbye, guys. You guys take care. Bye.